Hello everyone, welcome to a new video on electromagnetic fields. In today's video, we are going to see about an important topic, which is nothing but the electric fields from point charges to continuous distributions. As we all know, there are different charge distributions: point charge, line charge, surface charge distribution, and then volume charge distribution. A point charge is the smallest infinitesimal charge that can be represented as point charge, and line charge is nothing but the charges that are aligned on a tungsten filament that can be termed as line charge. Surface charge is the charges on the plates of a parallel plate capacitor, and volume charge is the charges on a bounded body. Any volume or any closed body can be termed as volume, and the charge distribution in that volume is called as volume charge distribution. So we are very much aware of these type of charge distributions. Now we are going to see about how the electric field will be in these kind of charge distributions. So here we are going to see about this is the agenda. We are going to see about the charge distributions and then electric field, how it is being calculated in these charge distributions, and then we'll have some analysis on this. First, we have two images. One is the point charge, the other one is the line charge. So in the point charge side, yes, a point charge represents a single isolated charge concentrated at a mathematical point of space. So the electric field for that is being calculated straightly from a Coulomb's law. So that can be E is equal to F by Q. That is the electric field of a point charge. So whereas continuous charge is a charge that is charges that are spread out uniformly or non-uniformly across a line or a surface or throughout a volume. So continuous charge distribution is any form other than the point charges, like line charge, surface, volume, or in any area. If the charges are spread out evenly or unevenly, that is called as continuous charge distributions. So this requires a different mathematical approach. We can easily, if there are n number of point charges, the electric field of these n number of point charges can be calculated by the principle of superpositions. Let the electric field across the charge Q1 be E1, and for the electric field around the charge Q2 be E2. Then if you want to calculate the cumulative electric field of these two charges, then it can be represented as E is equal to E1 plus E2. So the cumulative value of several point charges can be the consecutive addition of the electric field across each and every charges. But when it comes to continuous charge distribution, the case is different, wherein which we have to integrate the total electric field values. So here, for a line charge distribution, we define the linear charge density. We know that for point charge, you can directly write it as E is equal to F by Q, since it represents a single charge. But when it comes to continuous charge distribution, we cannot calculate the charge, but we can calculate the charge density. So here E can be represented as E is equal to F by Q, but here the Q is nothing but the charge density. We already know for line charge the charge density is rho L, and for surface charge the charge density is rho S, and for volume charge it is rho V. So we have to replace this value in the electric field equation. So we know that dE is equal to the electric field for differential length is given by dE, which is equal to 1 by 4 pi epsilon naught dQ by R square. Since if it is a point charge, it is simply Q by 4 pi epsilon naught R square. If it is a line charge, it can be given by rho L by 4 pi epsilon naught R square, that is being given here. If it is a surface charge, it is rho s by 4 pi epsilon naught r square. Here the rho s can be A vector into dA. For volume charge, it is rho v dv by 4 pi epsilon naught r square. So this is how you can deal with continuous charge distributions, because we cannot simply sum up the electric fields from individual point charges. So we have to divide the continuous charge distribution into small charge elements, which is nothing but infinitesimal values, and then we have to integrate their contributions to the total electric field. So now we can consider a line charge. For example, we can take one form of continuous charge distributions, which is nothing but the line charge. So let us assume a tungsten filament, which is nothing but like a line. Okay, so if we consider this line, finite line segment carefully, we can understand the vector components. So in this line segment, let the length be L and the axis be X, and it is centered at the origin with uniform charge density, and we want to calculate the electric field at the point P located on the y-axis. So here we represents the dq as dx, because that is the axis towards which the line is being projected. So the position is x, 0, 0, and the components for deriving this electric field is dE and DER, and due to the symmetry, the x components will cancel each other, so therefore the y components alone exist. So by integrating, we can get it as L by 2. So here for this line charge, we can have the electric field equation as dE is equal to dL by 4 pi epsilon naught r square. Here this, rho L dL. So here the dL value is L by 2. Now we can have a symmetry about this electric field strength. So the geometry of this line charge, this continuous charge distribution, has a significant impact on the magnitude and direction of the electric field. So by utilizing this symmetry, we can easily simplify the integration calculations. So if we take line charges, the electric field lines generally extend radially outwards or maybe inwards from the line. So for an infinite long line, the field is purely radial and its strength decreases as the length increases. If it is a surface charge, for an infinite plate of charge, the electric field is uniform and it is always perpendicular to the plane. So the field strength will be always constant, and it is irrespective of the distance. So